Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're beginning to look at lipids. Lipids are naturally occurring organic compounds found in animals and plants which are insoluble in water, but soluble in nonpolar organic solvents. They're very important biologically. Examples of lipids are fats, oils, waxes, steroids, prostaglandins, terpenes, and some vitamins. As you see in this flow chart, the biochemicals of a living organism can be divided into two main groups. Those that are soluble in the aqueous or polar phase. These would include your carbohydrates, proteins, and nucleic acids. Proteins include, of course, amino acids. The nonpolar phase are those lipid molecules. Lipids, as I said, are a whole family of molecules that include fats, oils, waxes, and steroids. All those molecules that are not soluble in the polar phase. Now, we're going to begin our discussion of lipids by looking at a molecule referred to as a fatty acid. Fatty acids. Now, fatty acids themselves, are not lipids. They're actually the building blocks of several classes of lipids. So while they're not lipids themselves, they help in the construction of the lipid. In actual fact, only traces of free fatty acids are found in cells and tissues. There are over 100 different fatty acids that have been isolated from the hydrolysis of lipids. So what is a fatty acid? Well, it's a carboxylic acid, an aliphatic carboxylic acid. Now you may say, what does aliphatic mean? Aliphatic simply means straight chain. An aliphatic carboxylic acid possesses a long unbranched chain of carbon atoms. They usually have an even number of carbons, carbon atoms, somewhere in the range of 14 to 22 carbon atoms. Now they are biosynthesized from two carbon acetyl groups in acetyl coenzyme A. Acetyl coenzyme A consists of this, and we use CoA to stand for the rest of the enzyme. Many C18 acids, that is, carbon 18 acids, are unsaturated. That means they have double bonds. And the double bond is in the cis configuration, which is rather interesting because cis is usually less stable than trans. So once again, living organisms seem to be defying the natural order of stability. Cis configuration. The most abundant in nature are palmitic, and these are their common names, and I'll be showing you them structures. Oleic, Stearic, Linoleic, and Linolenic acid. So all these words end in acid. They typically are the most abundant fatty acids. Okay, let's take a look at some of these fatty acids. It's both saturated, unsaturated, and give the common names, their IUPAC names, and their structure. The first one, we're going to begin with the common name that we're going to look at is lauric. The IUPAC name for lauric acid is dodecanoic acid. So the shortest chain one is actually at our maximum in our nomenclature that we've actually covered. Dodecane was as far as we've taken it. So we're going to actually extend our IUPAC nomenclature a small bit. And of course the structure is CH3, CH2 10 times, straight chain, 10 CH2s, and then a CO2H for a total of 12 carbons. Our next acid is myristic, and you're responsible for the names and the structures of these lipids. Notice that we go up by even numbers. This is called tetradecanoic. Tetradecanoic is 14 carbons. So exactly the same as previous structure, except now we have a straight chain with 12 CH2s. We can keep going. Next one is palmitic. Palmitic acid is hexadecanoic. Hexadecanoic acid. And of course, there are now 14 CH2s. Next is stearic acid. And as you might guess now, this is octadecanoic. All one word. Sorry about that. And that means 16 CH2s. Which brings us to the last one, Arachidic Arachidic acid has 20 carbons, so there are 18 CH2s. What do you think the IUPAC name is for a 20 carbon chain? In fact, a 20 carbon chain is referred to as acosane, and so this becomes acylcenoic acid. And these are the fatty acids that are saturated, that is, possess no double bonds in them. These are all the saturated fatty acids, common name, IUPAC name that you need to know. Now, I'm going to start looking at the unsaturated fatty acids. Okay? Now, and I'm going to begin by drawing their structures and putting their names above them because we need more room. Remember when you see a double bond, it is in the cis configuration. So we have CH2, 5, and then we have a CH, double bond CH. And that's in the cis configuration. We have 7 CH2s. And then a CO2H. So at carbon 9 from the carboxylic acid, 1, 8, 9, we have a double bond. 10, and then 16. What was the 16, the common name for the 16 carbon chain saturated fatty acid? Well, that was palmitic acid. Well, when you have 16 carbons in a saturated double bond based on palmitic, it is referred to as Palmitoleic acid. Because it's only one double bond, I don't need numbers. I can just say Z for cis. It's the Z configuration. And it's at carbon 9. So Z9, if you like. Hexadecanoic acid. Okay, now what happens if you keep the one double bond at carbon 9 but you add 2 more carbons? Based on stearic acid, this is given a special name, and it is called oleic acid. Oleic structurally is identical to palmitoleic. The only difference, you have a CO2H, a CH27, CH double bond CH at carbon 9, and then instead of 5 CH2s, we have 7. And if you have 7 CH2s, then that becomes oleic acid. Just like palmitoleic acid, it's Z and that carbon 9, but no longer hexa, it's octadecanoic acid. One word. Okay. So, palmitoleic and oleic acids have a single double bond in them. Now let's begin increasing the number of double bonds. As you start increasing the number of double bonds, we start adding the prefix lin in front to a common name, and you'll see linoleic, acid is related to oleic, palmitoleic. Let's take a look at linoleic acid structure. We've got CH3, CH2 4 times, and then we have a CH, double bond CH, CH2, and that's twice. And then a CH2 6 times, and a CO2H. If you like, if we were to draw that middle section out, let's make it a little easier to understand. You'd have CH, double bond CH, CH2, and then you repeat that, CH, double bond CH, CH2, and then the CH2 6 times, followed by your CO2H. Now, notice 1, 7, 8, 9. You still have the double bond to carbon 9. 10, 11, but you get a double bond to carbon 12. 13, 17, 18. Like oleic acid, this is an 18 carbon chain, but because it has two names, two double bonds is given different names. Your double bonds occur at carbon 9s and carbon 12, so in the IUPAC name we say 9Z, 12Z to indicate the cis conformation. And then we of course indicate 9, 12, octadecanoic acid. So you're responsible for this structure and its IUPAC name. Now, once again, if you have 18 carbons, but you add a third double bond, you don't have linoleic anymore, you have linolenic. So when you see linolenic acid, note, you have a third double bond. And let's draw its structure. CH3, CH2. Notice that 3 of these 4 CH2s are now grouped with this. You now have 3 of those. CH, double bond, CH, CH2. 3 times. And then your CH2 6 times. And your CO2H. To make it easier to count, let's draw this out completely. We have CH3, CH2, then we have a CH, double bond CH, CH2, another one CH, double bond CH, CH2, and one more. CH, double bond, CH, CH2, and then 6 CH2s, 6 times, and a CO2H. Now, notice that we have 1 carbon for the carboxylic acid, then 6 CH2s, that's 7, 8. We have a double bond to carbon 9, 10, 11, 12. At 12, 13, 14, 15, and 15. So what's the IUPAC name? Well, now it's 9Z, 12Z, 15Z, open brackets, dash, 9, 12, 15, octa, deca, Linoleic Acid. Make sure you know and understand these IUPAC names. Notice, octadeca means 18. It's based on decane, which is 10. Octadecane, right, is 18. So that's why the octadeca comes from. The last acid we want to look at is also an unsaturated. It has the most double bonds of all those that we're going to look at. Is Arachidonic. Arachidic acid was the saturated. Arachidonic is the unsaturated, and it actually has Arachidonic acid. It actually has 4 double bonds in it. Let's take a look at this structure. Now, I doubt I have room to draw it right across, so I'm going to draw the abbreviated, then we'll try drawing it. We'll see if we've got room. So, as before, CH, CH2, but there are 4 of these, leaving only 2 CH2s on this, and a CO2H. Let's try drawing that out. Probably we'll run out of room, but we'll try. So, CH3, CH2, 4 times. And then we draw our CH double bond, CH, CH2, and we do that 4 times. Go up to 3 times. Number 4. And then we have our CH2 twice. And then our CO2H. Just barely made it. How many atoms do we have in this? 1 plus 2 for the CH2s. That's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, plus 4 is 19, 20. So you see arachidonic is based on arachidic acid. Next to note is where the double bonds are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it looks like we have a 5Z, 8Z, 11Z, and 14Z. Five, 8, 11, 14. Now, what's a 20 carbon chain? That's acosane. What would it be with a double bond? That would be acosine. Acosadiene, acosatriene, acosatetraene, and then there's an oleic acid. So this is acosatetraene. Okay, and we drop the E and that becomes an oleic acid for the carboxylic acid. So there's the IUPAC name, and you are responsible for those IUPAC names. Now, as you notice, the common names are quite simple. The IUPAC names are quite large, and drawing the structures especially can be quite tedious. I mean, they are rather long chain molecules. So what we're going to do is come up with a shorthand notation for these molecules. Now, shorthand notation is designed to designate the length of the carbon chain, okay, the number of double bonds, and the position. Let's consider linolenic acid. Linolenic acid has 18 carbons. It has 3 double bonds. These double bonds are positions 9, 12, and 15. And you can check these. So we can represent such a configuration separating the number of carbons from the number of double bonds by a colon. So we would say 18 colon 3. We put a superscript delta, okay, which indicates the presence of double bonds. And the numbers are the locants, or where the double bonds are located, as a superscript. So 18 colon 3 superscript delta 9, 12, 15 tells me I have an 18 carbon chain with 3 double bonds located at carbons 9, 12, and 15. So this is the number of carbons. This is the number of double bonds. Delta indicates the presence of double bonds. And the 9, 12, 15 are the position of the double bonds. Okay. This has also been written in a different format. You will also sometimes find text writing a large delta with a superscript 9, 12, 15. Delta again indicates the presence of double bonds. and the 9, 12, 15 gives the position. Then right after this, in brackets, we have a carbon. The superscript number is the number of double bonds, and subscript number is the number of carbon atoms. So both shorthand notations have been used. What do you do when there's no double bonds? What would you say, for example, stearic, which has 18 carbons but no double bonds? The shorthand notation for stearic would be 18 colon 0. Or there'd be no delta, no numbers. It would be C18 0. Okay? So you can practice these designations, and some are given to you in your handout notes. Okay, so we have several ways of designating fatty acids. Now what's interesting is fatty acids are key constituents of fats and oils. They're found in everything from cocoa butter, lard, human fat, peanut oil, olive oil, corn oil, cod liver oil, etc. The constituent fatty acids comprise these oils in different percentages. For example, if you look at the composition of olive oil, for example, you'll find that it has a very low percentage of the saturated fatty acids. That is, it's only 7% palmitic and stearic, 2%, a total of 9% saturated. The olive oil has unsaturated oleic, 84%, linoleic, 5%. So 89% of oils is the unsaturated fatty acids. Whereas if you take something like lard, for example, the amount of saturated fat, or human fat, the amount of saturated fat is much larger than the oils. Now, while I'll never expect you to know these percentage acid compositions, they're interesting for comparison's sake, so I have provided you with a chart in your text or your handout notes. Now, note one important point. Mammals cannot introduce double bonds at carbon atoms beyond C9. So fatty acids that have double bonds beyond C9 would become essential fatty acids and must be consumed in the diet. Fatty acids are necessary precursors in the biosynthesis of many fatty acid derivatives. One example being prostaglandins, and we're going to talk about those in a moment. Well, let's begin looking at the first class of fatty acid. And this is a rather large section, so we'll probably be covering it in 2 podcasts. And as I just look at it, in fact, maybe we should break this up. I think this might be a good place to stop. Yeah, we'll continue with the classes of lipids. We're going to look at how the fatty acids are assembled, or how they're the building blocks for some of the lipids. And one of the first ones we're going to look at is the neutral acylglycerol. In fact, why don't we just introduce it, and then we'll carry on with the next scribblecast. Okay, so there are several different classes of lipids based on fatty acids. And one of the first ones we're going to look at is the neutral acylglycerol. Now, we already know that alcohol, such as ethanol, for example, can react with carboxylic acid, such as ethanoic acid or acetic acid, and in acid and heat, we can produce ester. Well, it turns out you can do much the same thing with fatty acids. And if you react the fatty acid with a triol, whose common name is glycerol, say we take 3 stearic acids. So we take 3 stearic acids, C17, H35. So we take glycerol, plus stearic acid, remember stearic acid is a fatty acid, not a lipid. We can form an ester off each alcohol group. This molecule has several names. It's called tristearoyl glycerol. It's also called tristearin and sometimes called glycerol, or glycerol, sorry. This one's much more consistent with our nomenclature for esters, tristearate. So, having established what fatty acids are, we now see that they can interact with molecules like glycerol to make what are called triacylglycerols. In the case of stearic acid, we make this glycerol tristearate. Glycerol tristearate is an example of a lipid, and it is also a fat. Now, while fatty acids are not fats, you can see how they combine with alcohols to form esters that are fats. Next Scribblecast lecture, we're going to actually explore neutral acylglycerols in more detail. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.